In this episode, we're going to make something that feels abstract feel concrete. Why automation breaks when dependencies drift, and how Dockerfiles help you lock down a predictable execution environment. When you are new, it is easy to think a script is the whole story, because the script is the part you can see and the part you write. In real operations, especially when cloud security controls and automation pipelines are involved, the script is only one piece of a larger system that includes the runtime, libraries, tools, and configuration around it. If any of those surrounding pieces change unexpectedly, a script that worked yesterday can fail today, or worse, it can run and produce subtly different results without making noise. The reason Dockerfiles matter is that they let you describe the environment your automation needs in a repeatable way, so anyone can rebuild it and get the same behavior, which is the foundation of reproducible execution. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A dependency is anything your automation relies on besides your own code, and that category is broader than most beginners expect. It includes the language runtime, like a specific version of Python, and it includes libraries your code imports, and it includes external tools your workflow calls or expects to exist. It also includes operating system packages, certificates, environment variables, and even file system layout assumptions that your script might never mention directly. In cloud security automation, dependencies are not just convenience items, because they influence how you parse data, how you validate inputs, and how you authenticate to services. When a dependency changes, it can alter parsing behavior, change default settings, or introduce new warnings that your automation misinterprets. Beginners often experience this as random breakage, but it is not random at all, because it is the predictable result of an environment that is allowed to drift. The deeper lesson is that automation stability requires environment stability, and environment stability requires a way to define and rebuild that environment consistently. Reproducible execution means that if you run the same automation with the same inputs, you should get the same outputs, regardless of who runs it or where it runs. That does not mean the world outside your automation is frozen, because external systems change, but it does mean your automation should not change behavior simply because the runtime or dependencies changed underneath it. In a pipeline, reproducibility is a safety feature because it allows you to trust the results you see, especially when those results affect security decisions like whether a control is enabled or whether a configuration is compliant. Without reproducibility, you can waste hours troubleshooting false failures that were caused by a hidden version change rather than by a real misconfiguration. It also becomes harder to prove that a security control was enforced consistently across environments, because the evidence depends on whatever tool versions happen to be present at the time. Dockerfiles support reproducibility by describing the environment as code, which makes it versionable, reviewable, and rebuildable, rather than an invisible set of assumptions on a machine. A Dockerfile is a recipe for building a container image, and the key idea is that the image includes everything needed to run your automation in a predictable way. Instead of relying on whatever is installed on a laptop or a server, you build an image that contains the runtime, required libraries, and any tools your workflow expects. When your automation runs inside that container, you are no longer at the mercy of a host system's package updates, configuration quirks, or missing components. This matters for beginners because it shifts your thinking from my code works here to my code works in the defined environment, which is what professional automation requires. In cloud operations, this is especially useful because pipelines often run on shared build agents, ephemeral runners, or managed systems where you cannot assume the environment matches your local setup. When you define that environment in a Dockerfile, you create a shared baseline that teams can trust. That shared baseline reduces operational risk because it eliminates a large category of variables that otherwise cause inconsistent behavior. A critical concept in Dockerfile-based dependency management is the base image, because the base image is the foundation of everything that follows. The base image determines the operating system layer, default tools, and sometimes the runtime you start with, and that choice influences security, compatibility, and size. From a reliability perspective, you want a base image that is stable and appropriate for your automation, meaning it supports the packages you need without carrying unnecessary extras that increase complexity. From a cloud security perspective, you also care about minimizing your attack surface, because every extra package is another thing that can have vulnerabilities and another thing that might behave unexpectedly. Beginners sometimes pick a base image because it worked once, but a safer approach is to pick a base image deliberately and to treat it as part of the dependency contract. A Dockerfile makes that choice explicit, which is valuable because it can be reviewed by others and adjusted intentionally rather than by accident. If your automation depends on particular system libraries or tools, the base image should support them without requiring fragile workarounds, because fragile workarounds tend to break in the worst moments. Layering is another core idea, because a Dockerfile is built as a sequence of layers that together form the final image. Each instruction adds a layer, and the order of instructions affects both build efficiency and how clearly the recipe communicates intent. For reliability, the most important point is that layers should represent stable steps that can be reproduced, such as installing required packages and placing your code in the image. When layers are designed thoughtfully, you reduce the chance of accidental changes slipping in, and you make it easier to reason about what is inside the final image. This matters in cloud automation because images are often built repeatedly, and predictable builds reduce surprises in pipelines. Layering also connects to caching behavior, where build systems reuse prior layers when nothing changed, which can speed up builds but can also hide issues if you do not understand what triggers rebuilds. A disciplined Dockerfile design is explicit about what should change and what should not, so you do not end up with an image that silently differs from what you thought you built. Predictable layers contribute directly to predictable execution, which is the reliability goal. Dependency pinning is where reproducibility becomes real rather than aspirational, because unpinned dependencies are a form of controlled chaos. If your Dockerfile installs packages without specifying versions, you are effectively saying give me whatever is current at build time, which means the same Dockerfile could produce different images at different times. That is the opposite of reproducibility, and it is a common source of automation drift where behavior changes even though your code did not. In cloud security workflows, this can be dangerous because a dependency update might change default security behavior, introduce stricter parsing, or alter how errors are reported, leading your automation to misclassify states. Pinning does not mean you never update, because it means you update intentionally, and intentional updates are easier to review, test, and roll back. A good mental model is that pinned dependencies turn the environment into a known snapshot, while unpinned dependencies turn the environment into a moving target. Dockerfiles make pinning possible and visible because the recipe can specify exact versions and can be stored alongside the code that depends on them. When your environment is a known snapshot, troubleshooting becomes simpler because you are not chasing a shifting foundation. There is also a security story inside dependency management, because dependencies are not neutral. They can contain vulnerabilities and they can change your risk profile. In enterprise and cloud environments, the container image becomes a deployable artifact, and that artifact should be treated as part of your security boundary. A larger image with many tools might be convenient, but it also includes more components that might have security issues, and it increases the chance that something unexpected exists inside the runtime environment. A smaller, purpose-built image reduces that surface and makes it easier to reason about what the automation can do and what it cannot do. This is not about fear, because it is about clarity, and clarity reduces risk. Dockerfile practices like using only necessary packages, avoiding unnecessary shells or utilities, and being explicit about what is installed support both security and reliability. When you can clearly state what is in the image, you can better validate compliance requirements and better defend the automation in audits. In cloud security terms, your image becomes part of your control environment, and Dockerfile discipline helps keep that control environment stable. Another operational risk Dockerfiles help address is environment mismatch between development, testing, and production, which is a classic reason automation behaves inconsistently. If you test automation on a laptop with one set of versions and then run it in a pipeline with a different set, you might see failures that are not about your logic, but about the environment differences. That mismatch can lead to wasted time and confused incident response, because people will chase the wrong root cause. A Docker file reduces mismatch by giving you one defined environment that can be used everywhere, so testing becomes more meaningful. In cloud security workflows, meaningful testing is important because you often need to prove that a compliance check or a policy enforcement step behaves consistently across environments. When the environment is the same, differences in behavior are more likely to be true differences in inputs or system state, which are the differences you actually care about. This also improves team collaboration because different people can run the same image and get the same behavior without spending hours aligning local environments. Consistency across stages is a reliability feature, and Dockerfiles are a practical way to achieve it. Configuration and secrets are a delicate part of containerized automation, and handling them safely is part of managing dependencies responsibly. It is tempting for beginners to bake everything into the image, including configuration values that make the workflow run smoothly. But that can create security exposure if sensitive values are stored inside an artifact that is shared. A safer pattern is to treat the image as the stable environment and the configuration as runtime input, so the same image can run in different environments with different settings. This separation supports reusability and reduces the need to build separate images for each environment, which can otherwise create version chaos. In cloud security terms, separating configuration from the image also supports least privilege and reduces the chance that secrets are leaked through image distribution. It also improves auditability because you can review the Docker file to see what is included, while managing sensitive runtime values through controlled mechanisms outside the image. The key concept is that dependencies belong in the image, but secrets should not, and confusing those categories increases operational risk. When you keep the categories clear, you get both reproducibility and safer handling of sensitive data. One of the biggest practical advantages of Docker files is that they help you create a clean boundary between your automation and the host system, which reduces unpredictable interactions. When automation runs directly on a host, it can be influenced by host-specific settings like locale, default paths, installed tools, and system-wide configuration changes made by other processes. Those influences are often invisible to beginners until something breaks, and then they are difficult to identify because they are not part of the script. Containers reduce this influence by providing an isolated environment that includes only what you defined, which makes behavior easier to reason about. This is especially valuable in pipeline workflows where the host might be shared and constantly changing due to unrelated jobs. When your automation is packaged in a container, you can treat the host as a generic execution platform rather than as part of your dependency story. That simplification makes troubleshooting faster because you can focus on the defined environment and the inputs rather than on hidden host variables. In cloud security automation, faster troubleshooting matters because delays in validation or enforcement can increase exposure. A strong Docker file reduces the number of unknowns, and fewer unknowns means safer operations. Versioning and change control are also part of reproducible execution because a Docker file is not a one-time artifact. It evolves as your automation evolves. The safe approach is to treat changes to the Docker file with the same seriousness as changes to the automation logic, because the environment can change behavior just as much as code can. If you update a base image or bump a dependency version, you should expect potential behavior changes, and you should validate them intentionally, rather than discovering them during a critical run. This is where the idea of a controlled update cycle matters, because pinned dependencies give you stability, but you still need to patch and update to address security issues. The discipline is to make updates deliberate and traceable, so you can connect changes in behavior to changes in the environment. When a pipeline suddenly behaves differently, you want to be able to answer whether the code changed, the environment changed, or the external system changed. Docker files support that clarity because they are plain text recipes that can be tracked over time. When environment changes are visible and intentional, you reduce both operational risk and the stress of unexpected surprises. It is also worth addressing a beginner misconception that containers automatically make everything safe and consistent, because containers only provide consistency if you are disciplined about how you build and use them. If your Docker file installs dependencies in a way that depends on the current state of external repositories without pinning, you can still get drift across builds. If you rely on implicit defaults or environment-specific behavior inside the container, you can still get inconsistent results across runs. If you treat the container as a black box and do not validate what it contains, you can accidentally carry unnecessary tools or insecure defaults that increase risk. The operator mindset is to treat the Dockerfile as the source of truth and to keep it clear, minimal, and explicit, because explicitness is how you avoid surprises. You also need to think about how the container is used in pipelines, such as ensuring that the same image version is used across stages when reproducibility is the goal. Consistency is not automatic, it is designed. Dockerfiles are the tool, but the reliability comes from the discipline you apply when you use them. When you connect Dockerfile dependency management to the rest of this course, the relationships become clear and useful. Primitive types and structured formats matter because your automation's parsing and validation depend on library behavior, and libraries live inside the environment you define. Fail-safe conditionals matter because you should stop or refuse to act when validation fails, and validation depends on consistent tooling. Iteration matters because repeated runs should converge on the same outcomes, and reproducible environments prevent subtle changes between runs from creating drift. Parameters matter because you want one image to run in multiple environments safely, with clear runtime inputs rather than hard-coded edits. Logs matter because you need evidence that the automation behaved correctly, and consistent environments produce more consistent logs and error patterns, which improves troubleshooting. Even topics like regular expressions and filtering become more reliable when the tools and versions handling them are stable. This is why dependency management is not a side topic. It is a foundation that supports every other automation skill you are building. When the environment is predictable, your automation can be judged on its logic rather than on its luck. As we wrap up, the central idea is that Dockerfiles are a practical way to manage dependencies so automation can execute reproducibly across machines, teams, and pipeline stages. They help you define the runtime environment as code, reduce environment mismatch, and eliminate a major source of silent failures caused by drifting tools and libraries. When you choose base images deliberately, design layers thoughtfully, pin dependencies, and separate stable environment from runtime configuration, you create automation that is both more reliable and more secure in cloud contexts. When you treat the Dockerfile as part of your change-controlled system, you make updates intentional and traceable, which reduces troubleshooting time and reduces surprise risk. On exam day, strong answers in this area usually reflect an understanding that reproducibility requires explicit environment definition and controlled dependency versions, not hope that everything stays the same. In real operations, the same understanding turns automation from a fragile convenience into a dependable capability that teams can trust. If you can manage dependencies with Dockerfiles in this disciplined way, you will be much closer to building automation that behaves consistently when it matters most.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.